Hi, welcome to Real Learning Center. Today we are actually starting a new topic called as light, and light actually is one of the most important topics in physics. So mainly because light, though it is so familiar to all of us, it still is something not well understood by scientists. So for a long time it has not been understood. Now there is some understanding, but even now today there's still a lot of research going on in light, which were quite intriguing and very difficult to understand some behaviors of light. So what we do is we are going to start with basically some properties of light that we know of. Okay, we know what is meant by reflection, refraction, some idea we have. So we'll start with some of these properties, and we will go ahead and see whether we understand them, why they happen, why is reflection happening, why refraction happening, what is that. They'll go later. Okay, when we talk about nature of light, we try to understand this. Initially, our aim is to understand all these different properties of light. Okay, so let's start with something very simple that we have actually daily seen. Let's look at this. There is a colorful rendering of a white light, and you can see the beautiful reflection there. And you can see here, this is actually a soap bubble, beautiful colors of the soap bubble. And you see your pencil actually bending. So what are these? These are the properties of light that we know of. Can you think about what they are? For example, you can see this one is dispersion. Now, light is actually dispersed. White light contains multiple colors, and this prism actually is separating them. And why does it separate them? We will see them later. See that later. And you see the reflection, and you also see this is called as an interference. It's probably new to you. So interference is a very interesting phenomena of light that we observe, and we need to explain it and how it happens. And refraction is bending of light that we have seen. So these are some of the properties of light that we know of. And there are a few more properties of light which are also quite new actually, if you see. The first one is a CD, which is actually looking colorful. And second one is actually, you can see, is a sun setting and giving us beautiful colors. The third one is even stranger. You can see that if you actually keep it in a particular direction, it is transparent. In another direction, it looks opaque. When you put two things, okay, they look transparent otherwise. So why does it happen? What is the property of light makes it happen like that? So the first one actually is what we call as diffraction. Okay. So what is this diffraction? We'll come to know. And second one is scattering. So we'll talk about scattering too, what it is. And then the last one is called polarization. So it is basically the light rays or light wave gets polarized. We will understand that too a little later. So these are some of the more exotic properties of light. Okay, so let's also study them in the due course of time. Now, if you look at some of these properties that I have mentioned, so rectilinear propagation of light, we know it is actually light goes in a straight line, and we have done many experiments even from the childhood to understand that. And absorption of light is something that we don't study much, but it happens all the time. So the light gets absorbed by the materials. We'll talk about that a little later. And then we know very well, we studied a lot about reflection and a little bit about refraction. And we also probably know the word total internal reflection. We'll try to understand it better. And then we have diffraction, interference, dispersion, polarization, and very recently the latest ones are called photoelectric effect. So many different. I have only listed let's say most famous ones. So you can actually look through and see there are many more properties of light. Once we know these things very well, the other things can be understood by using this. For example, if you see the total internal reflection and dispersion, both of these are an outcome of actually refraction itself. So if you study and understand refraction well, the other two things you will understand. So that what we will do is in this first session, we will concentrate only on reflection, refraction, and total internal reflection. So these are the three things we will understand in this session. And moving forward, then we'll understand dispersion and interference, all these in the next sessions. Okay. So let's start with a very simple thing that any material you take, okay, any material, if you actually send light to that, a part of the light basically gets reflected, okay, a part of the light goes through it, we call it as transmission, and a part of the light gets absorbed by it. So this is how the light always goes through in any material. In every material, this is true. Whether it is transparent or opaque, this happens. So now, the question is how much it happens. That decides whether it is transparent or opaque. In the case of a transparent material, we can see that it transmits more, okay, it reflects less and absorbs less. So most part gets transmitted. So that's why we call it as transparent. Whereas in the case of an opaque material, okay, it actually absorbs more. Opaque material absorbs more. Okay, it reflects also, sometimes more, sometimes less, depending on its color. And transparent is it transmits very less. It doesn't transmit much. That's why it is called opaque. If it transmits, then you can see the other side. If it doesn't, then you cannot see the other side. So that is why opaque materials are actually very less transmission. Though a little bit may be there that but we cannot see it so faint. Okay? So every material is like that. Now let's look at basically some important understanding of the absorption. So you see there is a red chair here. So I will ask you a question, a very trivial question, on why red chair appears red. You may say that it appears red, hence we call it red chair. Okay. So what really happens as per the light is concerned? So we know that the white light that we have from sunlight contains so many colors, all the colors, they are colors is what they say. So when that color falls on, such a light falls on this chair actually absorbs all colors except red. It absorbs all colors except red. Blue color it absorbs, green color it absorbs, all the colors it absorbs, but it reflects red only. Okay, so since it reflects red color, that red color light comes into your eyes and you see that it looks red. The reason it looks red is because it absorbs other colors other than red. So in such an, if that is the case, then can you think, for example, I will take this red chair, okay, and put it into a room. Okay, in the room, I close all the windows and I put it into a room and put some light, some blue light, only blue light, nothing else. So in such a room, will the red chair look red or something different? I'm not going to answer this question. So I want you to basically figure this out. Please take a red chair and take a blue light from wherever and try this and see whether you can still see it as red or something else. Okay, so let's go forward. Now let's look at laws of reflection. What are the laws governing reflection? We have seen the reflection happening on a surface. A light ray comes and reflects. So whenever a light ray reflects, that means that wherever the object is there, so suppose the object is on the other side, it reflects this side and we can see the object. Okay, so because the light comes into our eyes, then only we see the object. When the light reflects like this, it follows certain rules, some law. Okay, so we call it as laws of reflection. So how do we? So let's state that law. To state the law, what we need is we need a reflecting surface and we need a normal drawn to the surface. And that means a perpendicular line drawn to the surface. And this what we call, which goes like this, as an incident ray. It's called as an incident ray, and the angle it makes is called as incident angle. Okay. The incident means when it gets into, when it comes, what is like a it happens. So incident ray. So then there is a reflected ray which actually makes an angle R with the normal. So remember we are measuring the angle as a convention with respect to normal. We could have measured with respect to surface. We don't do that because surface may not be always flat. Sometimes surface may be bent, surface may be curved. So it's better to do it with the normal. That's why we do it. Okay. So now when in such a scenario it happens, first law of the reflection states that angle of incidence is equal to angle of reflection. These two angles are perfectly same. So that is the law. And then second law is interesting and important. Many people may not understand this. So there are three things here. One is an incident ray, one is a reflected ray, and another is a line that is drawn, that is normal line. So it claims basically that all these three lie on a same plane. What does it mean? They lie on a same plane means actually, if you actually draw a plane like this, okay, keep something, a book, okay, and you can see that all of them will be on the top of it. So nothing comes out of this. You can put one single plane and all of them will be on the top, exactly touching that. So that is called on a plane. So it one like this, other one like this will not happen. Okay. So this is the second law. And if you actually use this law, most of light reflection can be understood. At every single instant, remember that these two laws. And we can most often deduce everything else using these two laws. Okay. So let's go forward and see. So now, first question that comes to mind is, why can't we see our reflection in a wall? Okay, we go to a mirror and see ourselves. Very polished surface we see, okay, ourselves, but our reflection we can't see in a wall. Why is it that so? So basically, because the light does not reflect with the same laws? Are the laws of reflection different for the wall and different for the mirror? Not so. Laws of reflection are same for everything. So what really happens is that this one you can see is the mirror and the second one is wall. What happens is basically, even though we see wall as very smooth, it is not really smooth. At microscopic level, if you go and see, it has a lot of rough layering on the top. It is like a peaks and ridges like that. So because of that, what happens at that point to the normal, if you calculate on every ray that falls on the wall, it still reflects with the same law. But the surface itself is not really smooth. Because of that, the light rays go scatter everywhere and they don't come to our eyes clearly. In this case, the parallel rays neatly come to our eyes, and hence we can say that we will see the reflection. In this case, we will not. If we actually polish the wall very well, so that it is so smooth, you will be able to see your reflection even in the wall. Okay, so that is why we don't see our reflection in the wall. Now let's see what happens in the mirror. Okay, when we take a mirror image. So the question that is important to understand here is, how do we see ourselves in the mirror? And then what should be the size of the mirror so that you can see yourself fully? Okay, do you need mirror to be as big as you, or it can be very small? So what is the size of the minimum size of the mirror in which you can see yourself? Actually, if you see, even if you take a mirror and take it farther and farther from you, do you think you can see a bigger portion of yourself in the mirror? Try it out. You will not be able to see. You can only see the exact, that some amount of portion of your body, that's all in the mirror, smaller mirror. So you have to increase the size of the mirror to see yourself fully. Okay, so what is the, how do we say, what is the maximum, what is the minimum size of the mirror in which we can see ourselves fully? So let's understand that by looking at the way mirror works. Let's say I'm standing here and I'm watching the mirror. So when I'm watching the mirror, I'm seeing my image there. So what do I do? Or how am I seeing that? So I'm seeing my image means I'm seeing my body fully in the mirror, and I'm seeing my head, I'm seeing my legs like that. Okay. So if I have to see my legs, then the light that has fallen on my leg has to actually go and reflect from the mirror and come to my eyes. So that is what happens here. You can see a light that goes from the leg, goes to the mirror, reflects back and comes to the eye. So that is the ray by which I can see my own legs. And you can see my head, how do you say? Head, top of my head. That ray goes from the head and hits the mirror and comes back to my eyes. So I can see the head. So if if I have to see my leg, you have to see on the mirror there is laws of reflection holds good. That means angle of incidence is equal to angle of reflection. If the mirror is very small, then the light ray which hits the bottommost portion of the mirror comes back only up to my neck. So that I cannot see. It has to come to my eyes. For that to happen, the size of the mirror has to be at least half the size of my height. It must be half my height. Because when it comes back here, so how do you see the first of all image? The way you see is whatever our eye sees. So that ray we actually extend it back always. We means our mind. That is how we see an object. Whenever we see an object, how do we say object is there? Whatever light is coming there, we extend it back till we see an object. So that is why we see the object on the other side, inside the mirror, at the same distance as we are standing from the mirror. So you can see the image there. And the size of the mirror should be at least half our size to be able to see ourselves fully in the mirror. Now let's look at multiple reflection. I think you have seen many times that you can actually take two mirrors and some angle you can put them between them and you can see more reflections. Let's say in this case you can see three reflections, not two reflections. Third one is itself, object. Now you can also change the angle and now you can see three reflections. So can you get more? You can get 4, 5, 6, many reflections. So is there a way to find out? Now how does it happen? If given an angle between the mirrors, can you say how many reflections can we see? It is possible, and it is even possible to prove that, but I will give you an idea. Okay, so here actually number of images n say is equal to 360 divided by theta minus 1, where theta is the angle between the mirrors. If the angle between the mirrors, let us say, is 90 degrees, so you can very clearly see that 360 by 90 is 4. 4 minus 1 is 3. You can see 3 images. That is what we are seeing here. It's 90 degrees. Okay. If it is like 120 degrees, then the second one, okay, where you can see 360 by 120 is 3. 3 minus 1 is 2. You can see 2. So one thing you have to understand is that it is possible that the value n comes as not an integer. Then you have to basically round it up to the nearest integer. That's what you can see. Okay. And also remember that sometimes the images actually overlap in the sense that in the middle you can see wherever there is a corner there in the middle, two images are overlapping to give you one single image. Okay. So you can also see from the same formula that if theta becomes 0, that is parallel mirrors, you can see infinite images inside. In a parallel mirrors you can see infinite images. So this is some of the things that you need to remember. Now if you quickly want to calculate how many images, you should use this simple formula to calculate. Okay. So now let's look at, we have understood reflection to a good extent. I'll not go too much detail into it. Let's get into refraction. So what is this refraction all about? So we know reflection. Now we said that whenever a light falls on something, it both basically transmits, it reflects, it absorbs. So refraction is about transmit part of the light. So light actually comes, let us say, like this onto a glass slab. I have a glass slab here, and then I will draw a normal at that point. So perpendicular line at that point of incidence, and you can see that this is basically what happens to the light. Some part reflects, some part goes inside. Okay, so now we will name the angles. This is called incident angle between the normal and the incident ray, and this is a reflected angle, refracted angle, because it is refraction. Okay, we still call it R. Now that ray that went inside now also encounters basically another separation and go back to the air. Okay. When that happens, again it bends. You can see very clearly that this bending is actually equal and opposite to the first bending, in a sense that the angle with which it hits the other surface is actually R, because of the, you can see that alternate angles. And then when it goes out, it is BEI. Okay, this is an emerging ray, this is an incident ray. So those two angles will be the same. So refraction happens only when light actually enters, crosses a medium. Initially it is in the air, then it went into the glass, then it went back to the air. So whenever light ray goes from one medium to the other medium, that is when the refraction happens. If light is traveling in the same medium, it will not bend, it will always go in a straight line. Whereas when the light goes from one medium to the other medium, it bends. Okay? So that is what is called as refraction. Now the question basically is, how much does it bend? It depends on what. Okay, it bends a little bit or it bends too much. It depends on what. So the answer is basically it depends on a character called as refractive index of the medium. Refractive index of this medium. This is a glass. So its refractive index depends on that. It actually bends. So what is this refractive index? How do we calculate this? Refractive index is nothing but actually the speed of light in air or vacuum divided by speed of light in the medium, given medium. In this case, it is glass. So if you take this ratio is called as refractive index. You can clearly see here actually, speed of light in air or vacuum is the maximum. It is 300,000 kilometers per second. Okay, 3 into 10 power 8 meters per second. That is the speed of light in vacuum. And speed of light in the medium is always less than, any medium is always less than the vacuum. And hence denominator is smaller and numerator is higher. Hence the value will always be more than 1. Okay, so the refractive index is always more than 1. And when the refractive index is, when the light speed in that medium decreases more and more, yeah, then refractive index becomes higher and higher. So light bends more if refractive index is more. That means if you have higher refractive index, it bends more. That means if there is a bigger difference in the speed between air and that medium, then it bends more. In the junction, if it has to suddenly switch over the speed light, so to a great extent, it bends more. Okay, so why it bends, we'll see that in the theory, but this is the observation first. And we have also seen that if it goes from what we call a rarer medium to a denser medium. What is a rarer medium? Rarer medium is one in which refractive index is less. Denser medium is one in which refractive index is more. So whenever we use the word rarer and denser medium, okay, please understand that you should not confuse it with the density of the density and mass that we use. Mass is equal to density into volume. That density is different from this density. This is denser for only light. So it depends only on how light travels inside that. Hence, when you say rarer to denser medium, we have to understand that it is the refractive index that we talk about. If the light travels very slowly, then it is a denser medium for light. And if it goes very fast, it is a rarer medium for light. Okay, so that is what we consider. And it bends towards, so air is a rarer medium and glass is a denser medium. So when it goes from air to glass, you can very clearly see it would have gone like this. Instead of that, it has bent a little bit towards the normal. This is normal. Whereas when it is going away, going out of the glass slab, it goes from glass slab to air. That time it bends out. You can see that it is going away from the normal. So that is basically how it moves. And for understanding purpose, you can actually, we know that in the refractive index, sometimes we call it as mu, use a Greek letter, or we use normal English letter again. Vacuum is 1. Natural, because the ratio itself is a numerator vacuum, denominator vacuum. So it will be 1. And water is around approximately 1.33. And glass, in normal glass that we use is 1.6, some of them are 1.5 and 1.45, like that. Depending on the glass, it varies. And some of the very thick liquids also are slightly higher in refractive index. So we can very clearly see that here, for example, light, when you look at the refractive index, you can say light travels slowly in glass than in water. So that's just by looking at refractive index, we can make such statements because it is a ratio of speed of light. Now let's see what is the law of refraction. So in one of the laws is basically refracted ray and incident ray and the normal lie on the same plane like reflection. We will take it as granted. I'm not going to talk about that law. The law that I'm going to talk about is called as Snell's law. The scientist named Snell actually discovered this law. So what is this? So I'm going to basically take now general scenario. We'll not take air at all. We'll take basically medium 1 and medium 2. Okay, it could be water and glass, any medium to any medium. Okay. So light is traveling from in one medium and basically gets into the other medium. Now we draw a normal and we see how the light travels. So if it is bending towards normal, then we will say that medium 2 is actually denser than the medium 1. Denser means optical density. Okay, for the light, it is denser. Okay. So when that happens, we will actually name one of the angles as I, that is incident angle, the other one as R, which is refracted angle. And we say that we give a first rule. So what is that law? It says that you take the angle psi I and take a trigonometric ratio of sine on that. Sine I by sine R. Okay, if you know trigonometry, it's easier to understand. If you don't know also, I will tell you how to understand. Sine I by sine R, okay, is equal to actually speed of light in the medium 1 divided by speed of light in the medium 2. Okay, so it's generic. If for medium 1 could be air, in that case on the numerator you can write air or wall vacuum. Speed of light in the medium 1 divided by speed of light in medium 2. And we call it as refractive index of 2 with respect to 1. So this is n to 1. When I write, it means refractive index of the second medium with respect to the first medium. So that is what I am writing here. So n to 1. So n to 1 is nothing but sine I by sine R. R, you can very clearly see whenever I say n to 1, on the numerator we have speed of light in medium 1, denominator 2. So remember that. Okay, otherwise it becomes wrong. Then how do I understand this? Okay, it is about just bending, isn't it? So now I say I will draw a circle like this, and the circle centered around the point of incident. And when I do that, I will also draw two lines. One line where incident ray cuts the circle, second line where refracted ray cuts the circle. So let's name them segments AB and segment CD. So what is the meaning of bending more? Let us understand this. If there is no bend, if it goes straight, then AB will be equal to CD, isn't it? If there is bend, then CD's length will keep on decreasing. So the ratio AB by CD will keep on increasing. And that ratio is our refractive index, AB divided by CD, that's all. To say that in a mathematical language, we use this sine I by sine R. Okay, what is sine I? Sine I is nothing but angle I, if you take its opposite side divided by hypotenuse, which means you say AB divided by AO. And sine R is basically CD divided by OD. But OA and OD are same, they get cancelled. So you get basically AB divided by CD. So instead of saying that it bends more and AB is bigger than CD, the ratio AB by CD is nothing but refractive index. We use a mathematically more rigorous term called as sine I by sine R, but it means exactly the same, no difference. Okay. So this is basically Snell's law. So if the what it is saying is very simple. If the refractive index is more, it bends more, nothing more than that. That is all it's saying. Yes, that is Snell's law. How much it is bending? Calculate using this ratio. So now let us see something called as lateral shift. We have seen this just now, looking at a glass slab. Light enters, bends inside, then exits when bends outside. When it does so, you can actually see, if you take the incident ray and project it to the front, it would have gone like this if there was no glass slab. So what has the glass slab done to the ray is it made the ray shift a bit, and that shifting that bit is called as lateral shift. We measure it as D and name it as lateral shift D. So light was going, I just put a slab and it shifted. So that is a lateral shift. So this lateral shift, how to calculate how much it shifts, that can be calculated. You can derive a formula for that. But one thing that you see here is definitely the lateral shift depends on two things. One is what is the refractive index, how much it bent. Okay. Second thing is it also depends on the thickness of the slab. If there is higher thickness of the slab, there will be more lateral shift because it has traveled inside farther. Okay, so this it is possible to geometrically find out how much is this lateral shift with respect to, we know Snell's law, which is sin I by sin R is equal to refractive index, and we also know the thickness. We can compute. Okay, so this is, let us say, thickness. So instead of deriving that, I will give you the formula, but I think you can sit and use a sheet of paper and compute it. So this is given as, lateral shift is given as T into sin I minus R divided by cos R. Yeah, I and R are related through sin I by sin R is equal to refractive index. Okay. So you can calculate, given a refractive index and I, you can calculate R, and then you substitute into this, you will get the lateral shift T. So you can very clearly see that it is proportional to thickness T. So T is there in the numerator. This is one of the other important properties of light. And this is actually a derived property. It is based on simply refraction, but we call it as lateral shift, and sometimes you may have to compute. In many competitive examinations, you may have to compute the lateral shift. So then you can use this simple formula. Yeah. Another thing that happens is what we call an apparent depth. I think everybody probably would have observed. Even in the swimming pool, if you see the swimming pool bottom, if you keep something, it looks actually, its depth looks less than what it actually is. So why does that happen? Very simple. Now the light actually is not coming from my eye. Light is coming from the object, and that light, when it comes out, it bends away from the normal. Okay, when it reaches my eye, and my habit is to project it in the other direction straight. Okay, so when I project it, it looks slightly higher on the instead of on the floor. So the real depth, actual depth, is something, and the apparent depth is smaller. And you can very easily show it that apparent depth and real depth are related to how much it is bending. And how much it is bending simply depends on the refractive index. So the formula goes as, if you take actual depth divided by apparent depth, actual depth is bigger, apparent depth is smaller. So this ratio is higher than 1, and that ratio is exactly same as refractive index of, let's say, water in this case. So refractive index is equal to actual depth divided by apparent depth. So this is another nice formula that you can also derive, but you can easily remember. It will be, you can use it to calculate the depths in many different problems that you may solve in the exams also. Okay. So, but however, keep in mind that whatever you see from the top, then things appear nearer to you. Whereas here is what something you have to think. Suppose you are inside, then if you see something on the outside world, does it appear nearer to you or farther to you? Think about that. So think about a scenario where there is fish inside, and there is a bird coming to pick up the fish. Bird is coming near. and fish is looking at the bird. So now fish will see bird very near than actually what it is. Sorry, the bird will see the fish to be nearer than what it is, whereas fish will see the bird farther than what it is, and it thinks that, oh, the bird is still far away, and it comes to the top and gets eaten up. So think about this. Is that how it happens? So that is a very interesting understanding of apparent depth versus real depth. So you can draw some diagrams to understand what happens between the bird and the fish. Now let's see the another thing that we always talk about. Why do stars twinkle? This is again because of the refraction. What really happens is that the light ray, when it is coming into our atmosphere actually is continuously changing. Okay? When it is changing, the lot of warm air, cold air keeps moving here and there, and it so happens that the cold air is a little denser than the hot air, and hence refractive index is slightly different than vacuum. Then what happens is that there is bending. So when there is bending, and that bending keeps on changing, okay, you will see when you look at the sky, there's some light ray comes to your eyes, and you project it back and say there is star. But within the fraction of a second, the bending changes, and the ray comes back from a slightly different direction than before. You project that too to the back and say, oh, there is star. So this is as good as star is slightly in a small area, it is moving up and down and in all directions, and that is what we call twinkling of stars. And why do suppose if you go, for example, and go to space, maybe go to moon. From the moon, when you look at stars, they don't twinkle; they are just there. The twinkle, twinkle, little star doesn't happen in moon, only in Earth. And why do the planets not twinkle? That is because planets are actually nearby, and they are not point objects. Stars are very far; they are always simply one single point, and hence it keeps like moving. Whereas planets are a little bit more circular in nature, and you can see the light coming from both sides, even if they actually even those lights are also deflected like this because of the refraction. But since it is slightly bigger, we will see that its size is slightly varying, but it is never going to be moving so much. So that is why planets don't twinkle and the stars do. Okay, that is all because of the refraction which happens on the surface of on the atmosphere of the Earth. So now let us look at one more phenomena called as total internal reflection. It's a very interesting phenomena regarding refraction. So what do? We actually take, let's say, water and air, the two medium. Air is a very rarer medium and water is denser. So if I am having some light source inside the water, and if I take light ray going from there, it has to escape out. So how does it do? You draw again to be able to draw the diagram, we need this normal. Otherwise, light doesn't need a normal. Okay, it goes there, and then it goes away from the normal because you're going from denser to rarer. So that means that the incident angle is smaller than the refracting angle. It goes away from the normal. This is how it happens in any time when you are going from water to air. And how much it bends depends on the refractive index of water. Okay, if water's refractive index is known, you can compute actually what is the value of R. Now, what if I actually change the angle of incidence and make it a little higher? So increase the I. So definitely R also will increase. So I can increase I sufficiently and get the R to increase also more. And it is possible that I can take the I such that, okay, when I draw that, the R is almost 90 degrees. It's called greasing the surface. So R here is 90 degrees. This is at a particular angle of incidence, R becomes 90 degrees. Then if I even increase more the angle of incidence, then what happens? The light actually now completely reflects. There will be no refraction. All the lights gets reflected back completely. That's why we call it as total internal reflection. It reflects completely. And the angle, which is basically at which the angle at which it just grazes the surface of the water, the 90 degree, R is equal to 90 degree. That angle is called as critical angle. So whenever your angle of incidence is actually more than the critical angle, if it is higher than the critical angle, then you can be sure that there will be total internal reflection because all the light gets inside. So this is one of the very beautiful phenomena. In nature it occurs, and we use it even in technology for many important uses in communication systems and all that. So let us see what in nature, how is this used. So before going there, please understand here there are two rules. There are two conditions for total internal reflections to occur. The first condition is the light has to be traveling from a denser medium to a rarer medium. Otherwise, it won't happen. It doesn't move away like this. In a rarer to denser, it comes nearer to the, it never grazes the surface. So when you go from denser to rarer, yes, it actually gets into a critical angle. Now, first rule is it should be from denser to rarer. Second rule is that it has to be more than the critical angle. So the incident angle should be more than the critical angle. So then only it happens. So the natural phenomenon that we can see here is called as a mirage. So you must have seen on the road sometimes you can see that it looks like there's some water or oil spill on the road. There's a lot of water running on the road. Is it really there? There is no water on the road. It is just a mirage in the sense that we are seeing as though there is water. We feel that there is water, but there is no water on the road. How does this happen? Why do we think? Why do we feel that there is water? In reality, when you go nearby and see, it's a dry road, no water. Why does it happen? So it happens because of total internal reflection. We want to understand that. Let us say you are standing in a, it happens generally in summer, and there's a lot of summer heat. So during the summer heat, what happens is that the earth gets very, very hot, yeah, because of the sunlight, sun heat. And once earth gets very hot, land surface gets hot, it actually heats up the air which is very near to the surface. So the air which is near to the surface is warmer than the air which is at the higher levels. Okay, the cool air is on the top, warm air in the bottom. Cool air is actually a denser medium, as I spoke to you, and hot air is a rarer medium. Now, if you see, for example, a tree there or anything else, a sky sometimes, basically light from there comes from denser medium to the rarer medium. So, if the critical angle, if you are standing in such a way, that's why if you go nearby, it doesn't happen. If you are sufficiently far, then the angle it makes basically is what we call more than the critical angle, and then it bends and comes to your eyes. But we have this habit of projecting it back. So we project it and say there is reflection. So if you see reflection, suddenly your mind says that there must be water. So even sky gets reflected, and a bluish thing you can see, and you see here there is water. And it's a mirage. There is no water. It happens mostly in desert areas and such areas where people are desperate about water, and they see there is water and they go nearby, they don't see it. So it's called a mirage. So it's called chasing a mirage. Don't chase a mirage. It's not there. Okay. So, however, one thing you can see is that the light ray I have what we've written here is not like going straight and taking a turn like this. It is bending gradually. The reason that happens is that it is not just two layers, one cool air, one hot air. It's not like that. At every layer there is hotter when you keep coming, and it keeps bending many times, and that makes a curve. So that is why it looks like that. Okay, this is a mirage formation, and total internal reflection is responsible for mirage formation. And another thing which we want to understand is how do we use it in technology, as a technology. So say we call it as fiber optic communication. So there is a thin glass fiber, you can take a thin glass fiber and you pass a light ray through that. What will happen? Well, I will take small area of that and basically zoom it up, okay, and make it a zoomed area, that small fiber. Now, when light enters to through one is glass, the whole thing is, it's not a tube, it is actually full glass, solid glass. And inside is all glass, and outside is the air. Now, light actually enters inside here through one end, and you generally send actually very focused light. Okay, it's laser light. We use laser light. Once it comes inside, it hits a barrier between glass and air. So light is going from denser to rarer medium. And also, if you draw the perpendicular, the normal, and see, the angle of incidence will be actually more than the critical angle. If angle of incidence is more than the critical angle, then it actually bends completely, total reflection, total internal reflection, doesn't go out. So the bent light, reflected light, comes inside the glass itself, fiber. And there again it hits the other wall. And there same thing happens. It reflects again. Total internal reflection keeps happening and it keeps going. And it goes till the other end, kilometers, 20 kilometers, 30 kilometers far. It travels inside. It's like water going inside the empty tube. It is actually not even empty. It is a real glass, thick glass, solid glass, and it is going inside that. It doesn't come out, even if it bends. It need not be a straight wire. Okay, so that is the beauty of total internal reflection. That's how we use it. What is the use of this? Why, if light goes like this, what is the use of that for us? So what we do is that light is also an electromagnetic wave. So we will learn it a little later. But light is like radio waves, is also an electromagnetic wave. Like our mobile phone communication and our TV communication, most of this happens through electromagnetic waves called radio waves. So you can actually put in information like your internet information, your audio information, video information, and all the information to ride on this light. How it rides on what we call radio waves, it can ride on light, and that information can go through this. And on the other side, you can separate the light from the information and use it. So this is basically called as fiber optic communication. And to think about how effective it is, and if you take, for example, a copper wire and send telephone line communication to that, it will actually carry it has very less bandwidth. That means it can take some amount of information, a copper wire, whereas a fiber optic cable, which is very small in thickness, it is like, can you imagine what could be the thickness of this? This could be probably about 50 micrometers. So 1 micrometer is 1,000th of a millimeter. So it is 50 micrometers. And it can carry information up to around 10 gigabits per second. It is 10 Gbps. So that is the amount of information a single such thin fiber of 50 microns laid out for several kilometers can carry. That is the beauty of fiber optic communication. Most of the communication today for long distance is fiber optic. Okay, and you might have seen fiber optic cables coming as internet for broadband to your homes also. It's a fiber internet. Okay. So that is how we can use some of the very nice properties of light to our other uses. And this, you see, is a simple fiber optic, fiber based night lamp. It looks so beautiful. You put lamp there and you put these fibers, and on one side you are feeding the light and it is going through those fibers everywhere, and towards the end they will actually make sure that it's slightly opaque so that it lights up and you can see beautiful colors of light. So this is just another way of using the fiber optics, okay, for just keeping it as a night lamp. Looks really good. So last question that I'm going to ask is, does sun look bigger near the horizon? So we have always seen or heard and talking and people saying that actually when it is near the horizon, early morning or in the evening, sun looks bigger, whereas when it goes to the height, it looks smaller. And people give why is the reason for that? What is the reason for that happening? So people actually give many important scientific reasons, so called, saying that refraction happens, and because of the refraction, I don't know why, because of the refraction it looks bigger now. Okay. So however, what is important to understand here is that this is actually an optical illusion. Sun does not look bigger, looks bigger because of our own illusion. There are a lot of psychological reasons why it happens, but in reality you can actually measure the exact angle the sun subtends on the earth when it is there in the horizon or when it is there on the zenith. Zenith means top of our head. So horizon and zenith, in both places it is exactly the same size. So it is just an optical illusion. It never looks bigger. Looks bigger, but it is not really bigger. Whether it is horizon or, so if you measure it, it's just a question of optical illusion. So with that, we will actually come to the end of our first session, where we talked about a lot about reflection, refraction, and various aspects of refraction, and some formulae to calculate interesting things in refraction and its uses, total internal reflection, all that. In the next session, we'll talk about the new other property like dispersion, interference, diffraction, such things. Please come back. Thank you. Bye.